In this video, we're going to talk about the three most basic electronic components: the capacitor, the resistor, and the inductor. First up, the resistor. Resistors are probably the simplest electrical component. All they do is slow down the flow of current. They're just chunks of material that are less conductive than regular wire. How much the current gets slowed down is given by Ohm's law, V equals IR, where V is the voltage, I is the current, and R is the resistance. Resistors are commonly seen as a quarter-watt axial lead like this. Quarter-watt just means they're rated to withstand a quarter-watt of energy being dissipated through them. Since they inhibit the movement of energy, that energy that doesn't make it through has to go somewhere, and it gets turned into heat. If tons of current tries to flow through it, a lot of heat will be created, which will probably cause the resistor to fail. Here's one that's rated for 10 watts. It's bigger, so it can handle a lot more abuse and can dissipate a lot more heat. At the opposite end of the spectrum, here's a surface mount resistor. These are used because they take up less room by sitting on the surface of a circuit board. They can get really small. The smallest size you can buy is 01005. That's 0.01 inches by 0.005 inches. Here's one sitting on a grain of salt. These have to be soldered by robots because it's way too small for a person to do by hand. Here's another resistor that a lot of people don't realize exists. A 0 ohm resistor. Why would you want a 0 ohm resistor, you ask? Well, they're often used as jumpers when prototyping. That way you can make several configurations of a circuit by changing out the 0 ohm resistors with other values. It's also useful if you need to cross wires on a PCB but don't want to add another layer to the board. The other common use you'll see for them is configurations on special chips that sense the resistance on some pins and then change settings based on what it sees. Now let's look at capacitors. At its simplest, a capacitor is a thing that stores energy in an electric field. Functionally, it consists of two conductors separated by an insulator. In class, you'll almost always talk about a parallel plate capacitor, which is modeled by two sheets separated by air or some other insulator. In practice, capacitors are manufactured by sandwiching two long strips of metal between a dielectric and then rolling them up into a cylinder. You can think about the capacitor in a water analogy like this: a tank with one connection at each end and a rubber sheet dividing them in two. When water is forced into one pipe, equal water is simultaneously forced out the other pipe, yet no water can penetrate the rubber diaphragm. Energy is stored by the stretching of the rubber. In a real capacitor, the stretching of the rubber is the electric field. As more current flows through the capacitor, the back pressure, the voltage, becomes greater, and so current leads voltage in a capacitor. As the back pressure from the stretched rubber approaches the applied pressure, the current becomes less and less. It gets harder and harder to force more water in until eventually you can't anymore. So capacitors filter out constant pressure differences and slow varying low frequency pressure differences while allowing rapid changes in pressure to pass through. You can calculate the energy in a capacitor using this equation. Let's calculate the energy for this capacitor. This capacitor is rated at 16 volts and 100 microfarads. E is energy in joules, C is capacitance in farads, and V is voltage in volts. We plug in our capacitance and our voltage, which was 100 microfarads and 16 volts, and we end up with 0.0128 joules. Okay, let's try calculating something a bit bigger. This is a 3000 farad ultracapacitor. Yeah, 3000 farads. So we take 1/2 times our capacitance, 3000, times the voltage, 2.7 squared, and end up with 10,935 joules, or a little shy of 11 kilojoules. For comparison, defibrillators that are used to shock people back to life generally get charged to around 300 joules. So now that we have an immense amount of power at our fingertips, let's use it. So here you can see the power supply hooked up to the ultracapacitor, and the ultracapacitor is also hooked up to a multimeter so we can see what the voltage across the two terminals is. Here's the ultracapacitor melting some wire on the end of a resistor. Here it is melting some solder wick.
Oh damn. Wait.
And here's some magnet wire.
Isn't the quote though Raymond and...
Finally, we'll short it out over a penny.
Shoot you now, Hunter.
Yeah.
Oh.
The reason this stuff burns so easily is because so much current can pass through it. The datasheet here shows that for this capacitor, the short circuit current is literally over 9,000 amps. The other way to have explosive results with a capacitor is to reverse bias it. Certain types of capacitors, called electrolytic capacitors, have a fluid inside of them, and if the voltage is applied in reverse, they can fail catastrophically and explode like this. Finally, let's talk about inductors. Inductors can be kind of hard to get an intuitive feeling about. They're basically the magnetic version of a capacitor. They also store energy, but in a magnetic field instead of an electric field. Functionally, they're usually shown as a coiled wire. Here's what they look like if you were to go buy one. You can charge up inductors just like capacitors. You can use the water analogy to think about inductors too. A heavy paddle wheel is placed in the current of a stream. The mass of the wheel and the size of the blades makes it hard for the current to quickly change the wheel's speed because the wheel has so much inertia. But after a long time, it turns the same speed as the water flow. The mass and surface area of the wheel and its blades are analogous to inductance. Inductors filter out rapid changes in flow, while allowing slow variations in current to be passed through. The pressure difference, the voltage, across the wheel must be present before the current will start moving. Thus, in inductors, voltage leads current. It takes some practice in working with these components to get a good intuitive feel for them. Don't be afraid to experiment with real resistors, capacitors, and inductors either. Sometimes the best way to learn is to blow stuff up.